Hello, this recording is to demonstrate the testing of repeated measures of ANOVA within a linear mixed model structure using R, and to show how to plot that in Excel using R commands that generate estimated marginal means for certain models. I'll probably do two models, one simple model and one complex model, and then we'll call it a day. So first thing we need to do is have a database. Our database should be set up with subject and time. Now you can use time as a number or time as a name here. So the reason I've used time as a name here is because I want to compare the first block to the rest of the blocks later on. It's called a contrast. It's a fixed contrast analysis, linear mixed model. It's actually not really a name for it. That's my name for it. So what we're going to do today is we're going to look at balanced accuracy as a function of time, trait anxiety, and state anxiety, which are back here. Trait anxiety and state anxiety pre. Now we're looking at all of this in real, quote unquote, real non-normalized, looking at the raw values. That's because we'll want to plot these raw values on the balanced accuracy. You could do this with either raw or normalized values. The statistical test shouldn't be different. However, what may be different is the loadings on some of these, like pre-state anxiety and post-state anxiety. If you were to include a bunch of those in there, if the means are different, you'll have a little bit different interpretation of the factors. But we're not plotting those. We're not looking at the relationships there. So I'm just going to ignore that for now. My primary interest is in the outcome balanced accuracy. So let's get started. I'm going to shut that file. First, I should probably remember where it is. It is in my desktop working folder, October, November 2019, laser vigilance. So I'm going to open RStudio. And wait for it to load. They have a data set from previous analysis open here. I'll just shut that. I'm going to import data set from Excel. I'm going to browse to wherever that data set is. In this case, it's in one of these weird desktop folders I set up for myself. There's nothing special about them. They're just, normally I would try not to put anything on the desktop, but for these purposes, I'll just go ahead and do that, sorry. So there's our raw file. Now, some of the data is missing out of this, and the way you can tell that is there are NAs in there, and there's an NA here, you see here for one of the subjects and one of the blocks, and it automatically picks up that that's a character. So what we want to do is we want to make sure that it doesn't do that. And what we can do is specify in this box what our NAs are. It has to match what's in this box. Hit enter. And now you can see that those are double precision numbers, which is what we wanted. And import that. Now this has a lot of variables in it. I'm not actually interested in all the variables. I am interested in the subject column, the time column, the balanced accuracy column, and the state pre-anxiety, and then the state trait anxiety. So what I'm going to do is I'm going to go and pick up the correct libraries, which in this case we're going to be using LME4 as a package. I like to use LME test as well, LMER test, because I want some values on fit of the model, and it actually provides the Sather-Weight corrected. Well, you can specify whether you want the Kenward-Rogers correction for degrees of freedom or the Sather-Weight correction for the degrees of freedom. So far, I haven't found a major difference in those degrees of freedom calculations. They've been identical for most simple models. So I'm gonna name a model here. Normally what I do is I go back and look for something else that I've done in the past. So I've saved everything just to make sure that I'm getting the form right, because it's important to make sure that we get the form of these right, or one of two things can happen. The first thing being that it just doesn't work, or the worst thing is where it does work and we've done something, we've asked the computer to do something that we don't understand what we're doing. So in this case, I'm gonna start here with LME4 is the name. I'm gonna say laser vidge val acq-c, and that's going to be, I always put the entire form of the model in as the part of the name, just because it makes life easier for me. You don't have to do that. You can name them by number. I used to name them by number, but then I had to have a lookup table, especially when it gets really complicated. So there's time. So this is the simplest model we're going to run. So we look for our outcome. Our outcome in this case is balanced accuracy. So we go up back here, back up here, and it's going to want to name this one of the names of the columns. So balanced accuracy, all spelled out. You always want to model an intercept. There are many ways of modeling intercepts, but you know, at this point, I think just doing the regular intercept is fine. We're going to ask it to make a model as a function of time. So this column here. Now it'll come up with some weird thing that you don't need to worry about. It's actually a different type of test. And then we're going to do a repeated measures time test. And so it's within subject. That's what this means. This is the random effects part of the equation. This is the fixed effects part of the equation. This is the random effects part of the equation in parentheses, and that pipe, programmers call it a pipe with a vertical bar, means within, so one within, so each intercept is modeled for each subject. I think it also works on the slope a little bit. There are different types of modeling that you can do, but they get really complicated, and I'm not going to go into that. They're not useful. Well, they're useful for some things, and honestly, in some cases, I think they're useful for making statistics textbooks complicated. So, I mean, there are definitely uses for them. Don't quote me on that. So we need to put in our database, which is named database PSPH laser blah blah blah. So we've got laser pilot 051320 raw. Now what I'm going to do is I'm going to hit enter, and that's going to just create that object. Now if I want to take a look at that object, which I do, I have to ask it for a summary of the object. LME4 Oh boy, I've got a lot of them loaded. So laser, visions, balanced, accuracy, time. Looks like it's right. That's right. I'm going to look at this output. It does some, see this PR greater than T. These T tests are provided through the LMER test package. Normally, LME4 does not give you those. And it says here, shows you here exactly what that is. So if I highlight this guy like this, I can cut and paste this into a Word document, which is what I normally do. Just because I want to save everything and make sure that because it keeps a record of it, and you know, you'll have numerous commands that you run, and you want to make sure that you remember how you ran things. So it's frequent. We'll go back to notes. Another thing to say about this briefly is that the intercept is significant. Now, in some cases, when you have really complicated models with few subjects, the intercept is not significant. If your intercept is not significant, it's a good indication that your model is overfit and isn't accurate. So now what I want to know is I want to translate these t-test values and into something that everybody can understand pretty well. Because honestly, we could just report that these two time blocks are different than time block 1. Most people would not accept that. That would be perfectly proper, though, from the standpoint of a linear mixed model test, given the contrast structure here. We don't need to do an ANOVA. But because we're trying to communicate with everybody on an equal playing field, put in balanced accuracy. Now, I think the default on the ANOVA is the type 3 marginal, but I like to make sure that it's the marginal F values that it's given us and not the end of it. There are multiple different ways of calculating the degrees of freedom and the model F values. So sometimes you can have over the entire model variance, which tells you that by itself that factor would be significant, but it doesn't tell you necessarily whether in the model that factor is significant. So unfortunately, this is not technically significant. However, because it's a small sample size and it's trending, I'm okay with that. I would be perfectly happy to report 0.06 given the structure of this model. Now, and why is that? Because again, if you actually look at the model results, you have significant contrasts that are a priori hypothesized. Because basically in this particular experiment, we're looking at the psychological construct of vigilance. And that construct basically says, look, at time point 1, you're going to have less accuracy than at the time points past that. So even if I was to say, okay, well, I've got 3 contrasts here, technically I should use my threshold, p-value threshold as 3. Problem here is, of course, that you're already taking that into account by using the Seyss-Inquart correction for t-tests and the number of degrees of freedom. It's a compromise, basically. Now, what I'm going to do here is, let's see, did I copy that over? I never remember. Yes, I did. So I'll copy that over to my Word file. Now, there are several things that we can ask at this point. Now, a lot of people would say, well, you can't ask anything because you have a non-significant F value. And I would tell them, remember what I just said here. We hypothesize there's differences here. Even if I was Bonferroni correct by 3, divide 5 by 0.05 by 3, this is going to be real close to significant. If it's not significant, I'm not going to do 0.05 divided by 3. So 5/3 is what? I can't remember. I don't know. It's like 1/2 or 1/3. I could do a calculation, but I'm too lazy to right now. I'm more interested in actually doing the test that's going to give us some information we care about. And in that case, what we're going to do is we're going to ask the computer to ask R to make us some post hoc corrected contrasts. So what I'm going to do is, so 4. I'm sorry, my dog attacked my cat, which is not good of him, so I had to yell at him. Anyhow, so what we're going to do is I'm looking for a command here. Because there's a special way I want to do these tests. There we go. Okay, so this is a very complicated model. This test actually would not run the way it says that it is run. But so this is the multiple comparisons test and style of Tukey, which doesn't really mean anything to anybody, except for it just means it's pairwise. I think there may be some other special meaning. I'm going to give that time. So starting from the outside here, I'm getting a summary of GLHT, the general linear hypothesis tests on model. The model here is going to be the model that we just made. And this is a linear, I'm not real sure what linFARC means, or linFACT means. MCP, again, I'm not 100% sure. I got this off of biological statistics website. It works. So the test, then we can say, okay, we're gonna have this as adjusted. We're gonna use the home, so that's short for home SIDAC correction. That's a family-wise error correction, and it's, right, and now I've realized that I didn't load my libraries. So the libraries that I need here are multcomp, multcomp view, and I'm going to later use EM means or LS means, which they're kind of interchangeable. They're not interchangeable, but they work using the same command structure because someone went back and back coded the thing. So, okay, so we're going to try this again. We've got summary, GLHT, our model, general linear hypothesis test of our model. MCP time equals the Tukey, which is sort of like saying it's a pairwise test. Test equals the adjustment for multiple comparisons is the home SIDAC. So we're going to hit enter here, and what we're going to find is that there's only one trending, and like I said before, I'm pretty okay with that. That happens. I mean, it's because we have a small sample size. The sample size is 17. I know that doesn't sound small to a lot of people, but that sample size of 17 is not really enough to actually do anything with anything, but we'll see what happens. This is primarily for a grant, so hopefully that will be okay. Now, we can run another one and say that we don't want to adjust And I think none works. Also, LSD works, which is least significant difference, which are identical to each other. And in this case, that's fine. The Tukey being all pairs, we could actually say, okay, we're going to use this and we're just going to look at these because we're hypothesizing this one block, this first block, to be different. On the last data set I was working with, I couldn't do that because I was cycle phase, menstrual cycle phase, and that obviously there's no start place or stop place, so there's not really any a priori hypothesis about where that's going to be. Now, finally, we need to look up our EM means. And again, I'm going to go back to something I did before to get the code to make sure that I'm running what I want. So EM means is a pretty easy to use program. Literally, I think there's always all of these possibilities, weights, offsets, trends, and you can mathematically change those probably in almost any way that you want to if you really need to do that. We don't need to do that in this case. We're just using a very simple function here. And then I have a comma, and I'm going to tell it what it's, what are we separating by. So we're separating by time. It's the only factor in our equation. And here we get the accuracy over time. So what that puts out is they use the Kenworth-Rogers degree of freedom correction, which, like I said before, unless you get into really complicated models, I'm talking about like 5 variable with differential interactions and possibly subtracted interactions and you know, additive elements and stuff like that, then you worry about that. So, but I'm not worried about that, is basically what I'm saying. So here, you know, in this column, you have the mean, which is estimated marginal mean, which is estimated from the model. So it wouldn't be the mean if I was to just take the mean of that data. It's estimated from the model on the model fit. And that's actually the statistically correct way of doing it, given the factors involved, and we'll see why later. This is the standard error of the mean. This is the approximated degrees of freedom that it used. This is confidence interval. These are by default 95% confidence intervals. So you could plot just the 95% confidence intervals as an error bar. Interestingly, I don't believe these are symmetric. I believe that the default is to actually match the distribution now. So what we're going to do now is we're not going to pause and go back and do the Excel. What we're going to do is go all the way back to our model. We're going to make a more complicated model. So we've got all of the data here, blah, blah, blah. What I want to do is I want to add both the state trait anxiety pre-measure, and then also the state trait or state anxiety trait measure, or state trait anxiety and trait measure, which, yeah, it's a bit of a mouthful sometimes. So what I did here was I used this multiplication sign. Now I could look at both of these separately, which I'll do real quick, just as an example. And then I would say, okay, normally I wouldn't even look at the summary because this is gonna look, I mean, you can look at the summary. We'll look at the summary of this, but it's not gonna be horribly informative. I forgot to change the file. So let's go back and do that. So I'm gonna, oops, it's turning on sticky keys because it thinks that I'm crazy. So I'm gonna go back and fix this to what it was, and then we'll run that model again, but I'll change the model name to something that is reasonable, because I did not do that. Time, yep, there we go. Okay, now, there we've got time and state and trait anxiety. So time plus, I literally write this out, which is kind of weird, I know. STA pre plus STAT, or TRA, we'll say TRA because it's trait anxiety. Run that model again, just so we have it in our little path here. We're going to look at the summary of it real quick. We probably won't save a summary of it because it's not probably going to be too informative, but we're going to walk through it just as an exercise. So if you look at this, you still have your time blocks. Significant. Significance values are no different because this is additive. There's no effect, main effect of either state or trait anxiety. And that's going to carry on probably through what we're looking at here. There is a correlation, obviously, between state and trait anxiety. This is the correlation of fixed effects matrix. There's no real, I mean, there's correlation between time blocks, but there's no correlation between anything other than the state and trait anxiety. Now, I'm gonna take a look back. I'm gonna run an ANOVA now on this, just to see what's going on. So ANOVA, sometimes I get stuck in a loop here, literally. And so the time has had, all of these F values are non-significant. So what I'm going to do is I'm going to go back and say, okay, so I know that state and trait anxiety interact. We know that they're correlated. It says so right there. So what if I add the model of the interaction to that? And so since I'm adding the model of the interaction, I'm going to say times TRA. And what did it do? It failed to converge. That would be because we have a really small sample size. We're going to see if it ran anyway, because I think it did, and I think that should be okay. What we'll do is we'll run a couple of versions of it just to check. This is advanced troubleshooting that we've gotten to look into, because I didn't run this as a cooking show segment, which I should have probably done. So let me see if it gives me, allows me to get a summary. LME4, laser. Yeah, it failed to converge. It gives me a little note that it failed to converge, but we can see here why it failed to converge, because the interactions and all of this is so highly correlated that it's not making anybody happy. However, our intercept is significant. The more interesting thing here is that none of these are significant, which is fine. Usually it will fail to converge when things are not significant. So I'm going to run it just another time, because I'm going to fail to converge. Yep, same thing. Do we get the same data is the question. Do we get the same results? And it looks like we largely do. Yeah, so that's fine. Now what I'm going to do is I'm going to take the ANOVA of this. See if everything translates the way I think it might, or if it's accurate compared to the, yep. So we've got all that going on. See our degrees of freedom, dendrogram degrees of freedom are slightly lower because all these are tied up and they all co-vary with each other pretty strongly. So nothing significant here, which is not what I thought, but not what I remembered. But obviously, this is this data set that I need to be playing with. It's probably response bias or something that's correlated. I have no clue sometimes. So what I'm going to do is real quick, we'll get the estimated marginal means. Let's see. So this GLHT, this general linear hypothesis test, should work with this model just the same because time is separated out from the rest of those factors. Let's test to see if that is correct. So we get this guy, I'm going to do that. We're going to say this, and we're going to, I don't want to go all the way to the top. Come on. Go all the way down. And set this guy in here. And now you see why I don't include everything, because there's all that garbage in there. But guess what? Everything's the same because we're not asking it to interact with time at all. If we were to ask for an interaction with time, likely one, it wouldn't solve, and two, or it would not converge at all. This is not converged, but parts of it have converged, as you can tell, because we have the same results for the time factor. And then again, we can do the same thing with estimated marginal means, which I should not have to go back and look at because it's really simple, but I'm tired and I haven't looked at this data enough to know exactly what to expect when I run it, and I don't like surprises. And I just was surprised. So there, so that's this. And interestingly, our standard error of the mean is going to be a little different because we've tried to model more into our model more factors into our result. And so both the estimated marginal means are different and the standard error of the mean is different. And that largely depends on our degrees of freedom. We'll have slightly larger error bars, as you can see here. This is a negligible effect. So now that we've got this done, we're going to save that. So I'm going to save it on the desktop as time series example EM means, etc. Just do the date because it's my MO. So what I'm going to do now is, now that I've saved that, that's all well and good, I want to take a look at how to make the plot all the way to PowerPoint. So first thing we're going to do is we're going to have a mean. We're going to have a standard error of mean column. And what we're going to do is we're going to have block 1. And then I might pull this down if I'm super lazy and it works right. Yep, it works right. Just pull that down. Now I go back, look for, so I'm going to use this top one because it's more accurate, because it doesn't try to make sense of the trait and state anxiety, which for some reason are not significant, which I thought they were, but I have to take a look. It may be a different context than I'm thinking about. So I'm gonna put in the standard error mean because it's the same, 0193. All 4, that's great. Go back here. So I've got 0.734. Then for block 2, I have 0.717, 0.717. Block 3, nope, looking at the wrong thing. I have 0.691. Block 4, I have 0.699. And that gives me what I want, basically. Now, what I'm going to do is I'll highlight those 4. I'm going to have to move this god-awful viewing bar, screen sharing bar from Zoom. I'm going to go to Insert. I'm going to go to Insert, thank you. I'm going to go to Charts, and I'm perfectly happy with the recommended chart that they're using. So that's great. First thing I do is I delete a bunch of elements because Windows is element heavy, I guess, on their charts, you could say. Delete that title. Delete the lines. I bolden all the axes and make them black because this is a gray font by default. Not the grayest of grays, but it's gray enough for me to notice the difference. Blacken that, bold that. I'm gonna make that font a little bit bigger. I'll make this font probably to 10 is at least good. Now, this is the part where things are, I mean, this is not difficult, but I'm gonna change. So what I've done here is I've clicked on these bars. You don't want to click on them individually. You want to click on the whole thing, go to Format. Actually, you want to go to Chart Design, sorry. Go to Chart Design, drop down, looking for the error bars section. Go to More Error Bars Options. Go down to this. What we're going to do is we're going to have custom error bars that are based on our standard error of the mean. Now, its default is to start off with a 1, so you get this really ugly stuff, but you don't have to worry about that. So you hit on, what did I do now? So once I hit on custom, it makes this weird thing. I specify the value. I highlight these columns because this will give me the exact values that are adjacent to those bars. So we've got positive and negative standard error of the mean bars. That's great. Looks great. Next thing we want to do is change its appearance, make it black, and then we're going to make them about twice as big. I usually go from the default is 0.75. I usually go to 1.5 point. The final thing that I'm going to do is change the color of the fill on the error bars. Or not the error bars, so the bars themselves. And so I just realized that I'm doing this for the menstrual cycle study and not the SCT laser signal detection theory study. So I actually do want to change the plot because I don't want a bar plot, but it's virtually the same thing. I'm going to actually go back and delete this and start over, but it's not a big deal. So I highlight my block and row or column containing my mean. I go to here and I say, hey, I actually want a line graph because block 2, block 3, and block 4 are always going to follow block 1. At least that's my rationale. Delete this guy. Delete the lines. There's a border around here, an outline that you can make no outline. Normally I also, well, I guess we can keep the white. It doesn't really matter to me. Sometimes I delete out the white. Now we're gonna go and go home, increase the font size, make it bold, make it black. Block, bold, black, bold, bigger. Color of the line, I'm going to change it to some weird gray. Good enough for me. Go back up to chart design, add chart element, add error bars, more error bar options. Go over here to this column thing and go all the way to, well, I don't even know what that, oh, it says error bar options. Custom, specify the value, highlight SEM, highlight the other SEM, and then we're going to make the error bars a little bit bigger and black so that they contrast with the actual line. And that's that. There are some other things I would do. Well, that's that for that. Give me 1 second. We'll figure something else out. Give me just 1 second. We're going to add confidence. We're going to add significance bars in PowerPoint. But first I want to change the color of this axis to black as well. So I've got all that. Next thing I do is try to move this little guy. And I open up PowerPoint. So I'm going to open up PowerPoint. Just need a blank presentation for this. Delete. And I'm going to copy this guy over. The good thing about this is that if things get really screwed up and you need to modify something, like for example, I'll show you. What I'm going to do is I'm going to bring it over, and normally what I would want, it's going to give me design ideas, which I'm going to reject wholeheartedly. I'm making this big just for demonstration purposes. Normally I wouldn't make it this big. But I'll make this big as well. So you can see that I can manipulate the individual chart elements on here. If you were to copy and paste it as an image, you wouldn't be able to do that. So one thing I'm going to do is I'm going to manipulate this axis. And I'm going to format the axis, which I can now do in this, and it comes up in PowerPoint. Delete, I'm going to make the minimum 0.5. So 0.5 would be chance in most people's mind. It's technically not, but I'm not going to get into that. And so you can see there's not really any difference over time. And that is consistent with our F value of 0, 0, whatever, or 0.6, I guess, was the P value on that F. F value is somewhere around 2.6 or something. However, if we don't correct for post hoc comparisons and we say, okay, we're going to start with this, we're going to go with just these 3 comparisons. So block 1 versus 3 would definitely be significant, 0.01, and block 1 minus 4 would be kind of sort of significant. We're going to pretend both of them are significant and both of them we're going to pretend are differently significant. And you'll see what I mean when I get there. So I go to Home, Shapes, Line. Gonna make a line here. So what I want is I'm gonna, for one, I don't want that. I want that to be, yes, thank you. What I want is eventually I'm gonna want a line that runs from here to the middle between the 2 points here at block 3 and 4. From 1 to the middle of block 2, 3, and 4, because what I'm gonna do is I'm gonna make something that comes down and bifurcates, saying that 1 is as compared to 3, 1 as compared to 4. There's some significant difference there. So what I have to do is I have to make that line. I have to measure the line, sort of. So what I'm going to do is that. It's pretty much right on that line. On 1. There, it's not quite here. So what I'm going to do is I'm going to guess. I'm going to ask myself, is my guess correct? It's pretty close. So what we're going to say is that this is at 4.45, and then we're going to measure the distance to this guy. Which is less than that. Oh, it's 6.7. So 4.45 minus 6.7. I'm going to grab my phone here. 6.7 minus 4.45 equals 2.25. I'm going to divide that by 2 because we only want to go halfway. And then so we're going to have 4.45 plus our answer, which is 5.575. So what we're going to do is we're going to make the length of this line 5.575. Now, likely it's not going to allow me to do that exactly, so what I'm going to do is I'll just do my best. 5.575, yeah, 5.58, good enough. Now, I do want to change the look of that line because it's kind of nasty. So, oh, that's not right. Oh, so size, that's what I'm looking for. Okay. Line. I don't want it blue, I want it black. And I don't want it 0.5, I want it probably 2, or usually what I do is I do about 50% more than the error bar thickness. So normally it will be 2. Because this is such a large format, that probably wouldn't be what I would stay with, but for our purposes here, I'll live with that. Home shapes. I got to make 2 other lines. Well, I got to make 1, 2, 3, 4, 5 more lines. However, 1, 2, 3, 4 of those lines are going to be the exact same little line segment. And I'm just going to put that guy I'll put it at 0.3. Normally I'll put it at like 0.2 or 0.1 even. Make him black, make him the same thickness as that one. I go back to here, and I'm just going to copy that guy. Now, this gets a little tiny bit tricky. It's not horrible, but it is a little bit tricky. I'm going to zoom. So I have this horrible habit of zooming on the panel over here, which I honestly don't even want it there. So maybe I can get rid of it. And then zoom in. Just do 200%. How's that? Okay, that looks reasonable. we got to find where we are, of course, because it's PowerPoint. Now, I've got this guy right here. What I want to do is I want to align him somehow with the, so I'm moving him and then I'm clicking him off of him. You can see he's aligned right now, but the question is, how is he aligned? Because you want to remember that so that all your lengths are the same. There. Okay, so it's basically, he's aligned so that he is directly adjacent to the bottom part of that other line. Now I'm going to move all these guys over to where I'm going to use them. And I got to move my field of view over as well. And then, okay, I'm good here. I'm going to put one guy here in the exact opposite place to that. Now, I will say that I have never, ever put figures together with anyone else other than myself. So if this seems like it's a terrible method, that's not my fault. People are always like, well, just do it. And it's like, okay, fine. There are thousands of steps that I can think of that have to be done, and every one of you people do them, but you don't think about what you're doing very well. So there's my diatribe for the hour. I have to have one an hour where my head explodes. So we'll have this line we need to make. And so you can see where I put these guys right on top of these error bars, because they're going to span from there to there. And I want to make a line now that goes between them. This looks actually pretty good, which is somewhat disturbing. It's never that good. We'll make it bigger. And black. And it looks so uneven, but I know it's not. That would be perceptual distortion, I believe. So I'm gonna make that guy go up here. Come on, come on, come on. Now, it doesn't really matter if you find it easier just to put the ends so that this guy's over, it doesn't matter. As long as it's the same and the heights look the same, and honestly, the heights are the same, which would be nice, which you can do. You don't need to measure anything. You just eyeball it, basically. So there's that. I'm going to go a little bit over so that I can eyeball my correction. Got one more. That should be that. Now I'm going to go zoom back out, fit window. I don't know if that's straight or not. It looks kind of crooked, but I think I'm also really tired, so that might be the issue. Now, I'm going to select all this together. I'm going to group it. Because what that's going to let me do is take a look and move it however I want to. So see, I can move it up and down here. It ain't super great with alignment, but again, you can spend hours if you'd like to on aligning things. I don't necessarily. Sometimes I spend more time than I should, probably, but that's neither here nor there. And so final touch here is to indicate what kind of significance it is. So to do that, we need to insert a text box. Insert text box over here. We're going to just type a star. Make that text box a little bit smaller. And frequently I will change the size, make it bold, make it a little smaller. And then I'm going to copy that guy. Copy. And I need a plus. So what I'm going to say is I'm going to say this one is significant at 0.05 or less. I'm going to say this one is trending significant. There's a trend toward significance. So the p-value is somewhere between 0.05 and 0.08. That's my best judgment from reading an enormous amount of literature on what is and is not significant as to what is and is what is considered as something that is trending toward significance. Now, in truth, this was significant in the simple tests, but not significant in the more complicated tests. But just for illustration purposes, I'm going to do that. Normally what I do is I will make it 1 or 2 arrow points up above that. And that's that. You have to label the axis, which is a text box. I don't really have anything to say about that. You rotate it by using this weird rotation thingy. Usually center it, makes it a little easier. I might make it the font a little bit bigger and relative to the axis number labels. And then we have, it's now a time course plot, shows significance between these differences between these things. And I think that's about it. I'm going to end this right now, and I will send a link to it. Hopefully that helps. Like I said, again, this is out of proportion because I'm just showing what I'm doing here. You can change these line thicknesses however you'd like. In this case, really to be proportionate, I would make it really big comparatively. But again, I've also blown it up to the entire size of the slide, so I don't care. I'm just going to ignore that, and I'm going to end this, and we will convert.